A balloonist is directly above a straight road 1.5 miles long that joins two villages. She finds that the town closer to her is at an angle of depression of 35 degrees, and the farther town is at an angle of depression of 31 degrees. How high above the ground is the balloon? So just here's another example of where being able to solve triangles in real life applications can be very useful. Now, this is kind of unrealistic. It's one of these typical unrealistic textbook problems. I mean, so how is this balloonist, how is she finding these angles in the balloon? I guess she has one of those surveying devices. Why would she want to do this? But just trust me that in definitely in engineering, and I can imagine even in chemistry and other situations, being able to solve triangles, find lengths, etc., is very useful. Okay, and so what we learned in this section, we were introduced to the law of sines. And so like we already know how to solve right triangles using trigonometry, right triangles, if we have certain information. But now we're learning how to solve any kind of triangle we still use trigonometry, but we take advantage of the law of sines and the law of cosines to solve oblique triangles or non-right triangles. And so up to this point, we've only learned about the law of sines, and mainly in the non-ambiguous case, where we've got two angles and a side length to work with. But whether or not this is the side length included between the two angles doesn't matter, because once we have two angles, we can automatically find the third angle, right? Because the sum of all the angles is equal to 180. And then we have a side length, and it's included between any angles we want. So, okay, so let's see how we can use the law of sines to solve a triangle here. So, okay, the balloonist is directly above a straight road 1.5 miles long that joins two villages. She finds that the town closer to her is at an angle of depression of 35 degrees, and the farther town is at an angle of depression of 31 degrees. Okay, so we want to solve for this. Okay, well, let's see. We can automatically, we have, so 90 minus 35 is 65. 90 minus 31 is 69 degrees. Okay, so we've got this angle if we need, and we have a side length. So, okay, that's only one angle and one side length, but I'm imagining they're going to want us to use these right triangles here. So we've got one angle and a side length, but that's not quite enough to solve the triangle. So let's see. Okay, we've got two parallel lines here cut by a transversal, this transversal and this transversal. So let's see. These look to be opposite interior angles, right? Yes. So this has to be 35 degrees. And now we can sum the angles of the triangle to get this, but this should be with opposite interior angles 31 degrees, but let's check. We can verify this. So let's do 65 plus 69. So this angle should be 134. So 180 minus 134 minus 35 should be 31. 180 minus 134 minus 35 is 11. Let's see. So 90 minus 35 is 55. Okay. I screwed that up. Okay. And then 90 minus 31 is 59. I'm going crazy. Okay, so this should be 20 degrees less. This should be 114, I believe. Yeah. So, okay, so 114 plus 35 plus 31 should be 180. There we go. Okay. So, yeah, we can use the non-ambiguous case of the law of sines. We've got two angles and a side length, but with two angles, you automatically have the third angle. So, okay, sine of 114 over 1.5 Well, wait a minute. What are we going to do with? We're trying to find x, but we don't know. We can't just say 1.5 divided by 2. It tells us that there's one town is closer than the other town. So these aren't going to be the same length. So yeah, we can just use the law of sines to get one of these side lengths, one of these hypotenuses, and then use regular trigonometry to get x. So okay, let's call this y. So we'll say now sine of 35 degrees over y. So we're analyzing this outer triangle here, this triangle, oblique triangle. So, okay, y is equal to, if we cross multiply here, then divide by sine of 114, we've got 1.5 sine of 35 degrees over sine of 114 degrees. So 1.5 times sine of 35 divided by sine of 114. 0.941786 miles. So I'll just do 0.942 miles. Okay, but then just to conserve all these decimal points, I'll try and pull from this here when we do the calculation, upcoming calculations. So, okay, now sine, we see just regular trigonometry here with this right triangle. We see that sine of 31 degrees is equal to what? It's equal to x over that y value we just calculated. So x is going to be equal to y times sine of 31 degrees. So x is going to be equal to sine of 31 degrees, we're in degree mode, times this. And so you see it carries all those decimals, which is nice. And now we're at the end of the problem. Now we can go ahead and round it. You want to carry as many decimals as you possibly can with your computer or whatever, and round at the end. So the x is the height. That's 0.49 miles, about a half of a mile above the ground.